Okay, so uh, schedule again this week. No lab this week because you're hopefully working on these input modeling reports. I just want to emphasize that although I do want to see evidence that you have access to the system that you've picked, I'm not looking for all of your data right now. So, if you identify a system, you identify the general problem, like why you're, like long lines or some sort of complication. And then you sort of say, well, in order for me to model this system, I'm expecting to have these inputs. And then I might also not model, but I might also then capture these outputs for validation to sort of see if my sim is working well. And then of those inputs, then show me that you've gathered some of the data, like pick one of those inputs and then gather some data for like a short period of time, and then show me that you can fit a model to that. And so then that in whatever the 2 pages or whatever the format is that's online, that very quickly shows me, I see what problem you're working on. I see what problem you're trying to attack with this model. So I can give you feedback on whether it's too ambitious or maybe we need a little bit more. And then I also see some evidence that you actually have access to this system and you are ready to move forward with your input models. And then that will give me enough to know if whether you're ready to keep going on your own until the last week of classes, or if you need a little extra help. So I'm not looking for all your inputs, just looking for enough to allow me to assess that. So and so even for the input you picked, like you're like, we need to measure arrival time, service time, demand, all these different things we need to model, where you could say, well, I'm going to right now just pick arrival time. And I ideally would like to record arrival time for the 9 a.m. to 10 a.m. across all 5 days of the week. But I'm just going to focus on a 9 a.m. to 10 a.m. on one particular, Monday that I had access to this week, just to show that I, have pilot data to show that I have access to the system. So not looking for very much for this input modeling report to give you a lot of time for it, but enough for me to see that you're ready to move forward. And because after this, the next deliverable is your final deliverables. So that's the idea there. So any questions about what's required for this input modeling report coming up? Okay. And people have been emailing me about their projects, bouncing ideas off me, getting feedback. That's great to do. Please do that. I will get back to you as soon as I can, hopefully within 24 hours. So if you do need that feedback, you can come to me. The TA, the lab TA, has actually been around for this class a couple of times, so he's familiar with these projects too, and is a PhD student in industrial engineering, so can also give you some good feedback as well. So feel free to bounce those ideas off the TA. Part of the reason we don't have a lab this week is so you can kind of monopolize that lab time on your schedule and on his schedule for the work on this. So feel free to get input during these times. So that's this week. Next week, we'll go back to normal labs where more advanced topics in ARENA, how to use the output analyzer when you've got your sims, you're running your sims, and now you want to say, I've got 2 different types of sims, my as-is system and my intervention system. I'd like to compare them. The output analyzer will automate some of the stats that we'll start talking about next week. And then the advanced topics. So how do you actually run automated optimization like we did in behavior space for NetLogo? How do you do that for ARENA? Batching, like we talked about back in the muffin sim, those sorts of things, those will be covered in this lab 10. And if you're sort of, we got an automatic drop of 2 labs. So you might want to drop lab 10 or not, but something that's a hidden aspect of lab 10 that I mentioned last time is it's got almost a whole second labs of bonus credit on it. So there's a bunch of things that I would have liked you to have. I would have liked it a lot more, but there's just only so much time in the semester. So in lab 10, I kind of said, well, the first part of the lab, those are kind of like, some essentials I'm hoping you'll get. And then the add-on at the end, which gives you like 20 out of 30 extra points, or sorry, like so 30 points, the whole lab's like 30 points. And so it's an extra like 20 points that you can just skip. But if you do all of it, then this lab almost replaces another lab. It almost gives you another drop. So you could drop this one, or you could use it to help you drop another one or help you with previous ones. So just a heads up that Lab 10's got that extra bonus on it there. And then after that, no more labs. And so you can just use that time to work on your final project. All right, any questions about that schedule moving forward? Otherwise, same stuff I talked about last time. The final project, input monitoring report, that's what's due Sunday. It's 4% of your final grade. It's actually a big submission, but it is graded very lightly. So I look through those and I'm just looking for, it's an opportunity for me to give you feedback. There is a rubric. I am looking for certain things. If you have those things, it's more of a pass-fail sort of idea that as long as those components are there, then you're likely going to get the credit for that. There's some minor modulations for like if you did some weird things with your input modeling, there's some freedom for me to give to help and those to give me an opportunity to those who've done it really well to give them credit for that, and those that maybe need a little bit more feedback, a little bit more of a summative assessment to penalize a little bit for that. But most of this is for me to give you feedback to say looks good, or maybe add a little more, or maybe, hey, I don't think you can get this done in the next couple of weeks. Let's pare it down and choose a subset of this problem. So that's the input modeling report. Otherwise, we've got ICAs left over, not many. So there's this J1, J3, and L. Then we'll end up having a final exam review ICA. Homework H has been posted, 2 questions. This first question, we already kind of covered a lot of that. The second question, we did just enough for you to do the second question from the last lecture, but then we're gonna do an extension of that this lecture that should also help with that. Then otherwise, the last homework is homework J2. It can't be dropped because we use it to capture some metrics on the course that go over many semesters. And so it's one of these ones where we don't distribute a solution set, and it also can't be dropped. It's also going to synthesize across the labs and the lectures. So it's going to be a little different, but that's don't count on that one being dropped because it can't be dropped. Okay, any questions? All right, so with that, happy Halloween. So the puns here, which there will be plenty in this lecture, is normal versus paranormal. This one, of course, has tails, which are too small to be a normal distribution. That's a paranormal or a ghost. And I actually think that this is a really good timing, and that Halloween is all about p-values. Halloween is all about the things that go bump in the night and deciding that we've detected that's a positive detection and not a negative. So we'll see that over and over here. So to set us up for that, just a reminder, we talk about type 1 error, alpha. That is how many positives, how many detections we're willing to tolerate that aren't real detections. So you always have to have some error. If you crank this thing down to 0, and this is like a physical law, if you have a test that never, ever, ever makes detection errors, it will just never, ever make detections. That's like a fundamental property. Likewise, if you have a test that has 100% errors, then it's just going to always make detections. And so this alpha is a threshold that we, as the analyst, can set in order to figure out what our balance is. And so most people in science set their alpha at a 5%, unless they're in certain sciences, like certain biomedical sciences, they might crank them way down. So there might be reasons where they want to be very careful about detecting effects unless they're actually there. In engineering, we often crank ours up because we tolerate, because we want to explore, because we hopefully have an R&D budget that allows us to do further investigations. And so early on, we actually want to catch anything that might be real, even if it's not, and then we'll filter those out in further studies. So this is a lever that you end up using when you do these empirical analysis. The way we implement these is all of our statistical tests output a p-value, which is if there was nothing to see, what is the probability that we would get these data or worse? That's our p-value. So if our statistical tests dump that p-value out, we threshold it with alpha, and that's how we end up configuring our test for the balance we want in terms of our error rates. So p-values are important, but high p-values are not a metric of fidelity, of a match. High p-values just mean that we don't have enough evidence to discriminate between the null and another hypothesis. That doesn't mean the other hypothesis is true. In order for us to make comments about that, whether whether the null is true, we have to worry about beta, our type 2 error, the lesser error that we don't talk about as much. But when we're talking about goodness of fit, it's really all about beta, because it's all about trying to find evidence that the model that we hope is there, that we think is there, is actually there. So beta is given that the hypothesis, the null, is false. So in a goodness of fit, it's given that the model that I want our data to match to is not actually the right distribution, then what's the probability that I'm going to incorrectly fail to reject it? And so, the simpler way of saying it is the beta is one minus the beta is our true positive rate. So if we want to be able to make a positive statement about, if we want to be very clear that when we make a rejection, that we feel confident that it is a rejection, then that's the statistical power, which is just the flip side of our beta. And so if you have a high-powered test, you have a low beta test. A low beta test means that if you didn't reject it, then probably the null is much more likely to be true. So if you have very little data, then you're not going to have high power. If you have very little data, your beta will be high and your statistical power will be low. So it's the sensitivity of the test. So tests have a natural intrinsic sensitivity. It's just the Anderson-Darling test has a certain sensitivity, which is much higher than the chi-squared test. The Kolmogorov smear, the KS test, that is in between the two of them, they're their intrinsic sensitivity. But then for any test, if you give it more data, you make it more sensitive. So eventually you give something enough data, it will be able to detect something. And so for any mixture of a test and data, you can figure out how sensitive it is. And that tells you that if you didn't detect anything, then how much can you count on that result? How much can you say, well, if I didn't detect something, then nothing's there. So alpha is about if we detect things, how confident are we that we detected them? Beta is about if we didn't detect things, how confident are we that nothing's actually there? So those are those two mixtures there, and we often put them at a table like this, where we imagine there are universes which are in the columns and outcomes which are in the rows. And we imagine a universe where the null hypothesis is true. So remember, in a goodness of fit, the null hypothesis is the thing you're trying to fit, the thing you're evaluating. I think these data are normal, so the normal is my null. Whereas if you're doing validation, like you're trying to say, does my simulation model match the real world? Then in that case, the null model is that they match. And if the sim is way off, then we should detect that there's a difference between our sim and the real world. So you have to sort of think about, what is my null here? So the null might just be that two models are equal. The null might be that a particular model, like the normal, is the one. But so if we imagine a world in which the null is true, then we can make type 1 errors in that world. And so in that world, what's the probability that we reject the null even though the null is true? And then the correct inference is 1 minus alpha. In a different world where the null is false, then the correct inference is our statistical power. And then the complement of that is our type 2 error. So primarily when we're talking about tests, we're interested in we just read across this row here, and we're interested in the type 1 error and the statistical power. And because the other row is the complement, that ends up filling out the whole table. But we just usually don't talk about alpha and beta. We usually talk talking, and from person to person, even though in the back of the textbook, sometimes it'll be alpha, sometimes it'll be beta, sometimes it'll be statistical power. But normally when we're just talking between analysts, we talk about alpha or type 1 error and statistical power. Those are the terms we use. But we effectively fill out the whole table because these are complements. So I can also phrase that in a slightly different way, where I can talk about I have my null hypothesis, but I can also talk about my alternative hypothesis. And so the book, I think, phrases it this way, where we have an alternative hypothesis, which is not the null. I think we have to be very careful about this because we're very specific about the null hypothesis is, but there's lots of things that aren't a null hypothesis. So it isn't always one alternative. It's just not the null. So if it's not a normal, it could be an exponential, it could be a Weibull, it could be lots of other things. And so we don't know specifically what the alternative is. Now, as we'll see with things like the t-test, we assume that it's all normal, and really we're just making an inference on the mean. So in that case, we don't have to worry about all the different alternative distributions there could be. The alternative is it's just an alternative mean. And that makes it easier for us to calculate statistical power for things like a t-test because we make assumptions about the data distributions. That's why we have to test for those assumptions. But in general, for any test, if we don't make assumptions, then we don't really know what the alternative looks like. So we have to be careful about phrasing it this way. That's why we typically try to phrase it in terms of the null, the thing that we assume if nothing else is going on, this thing is going on. That's what we mean by that. But this just basically flips the table. So when the null is true, the alternative is false. When the null is false, the alternative is true. Otherwise, everything's the same. Now, in some fields, or just in general language, when you're talking to people, this question of what is a positive and what is a negative can get flipped. Because it becomes more about the quality of the solution. If you want to detect, if you go to the doctor, very rarely do you want a positive result in the statistical sense when you go to the doctor. Because the doctor has a null hypothesis. Human physiology looks generally like this. They take data, they take a blood sample, get metabolites out of your blood or whatever, they do a breathing test, whatever, and they have a null model of if this is a normal human being, this is the distribution that normal human beings fall under. If they get a positive result in this framing here, then that means that you're abnormal. There is something that they need to further investigate. There is something that potentially you might be sick, you might have cancer, there could be lots of things that could be wrong. And it's sort of weird to call that a positive result. So when you go to the doctor, you want a negative result, but it's also weird to say, yay, I got a negative result. So, in these contexts, depending on your stakeholders, sometimes we flip the interpretation of positive and negative. So you'd say oh, you're negative for cancer. So that might be a way to say that you don't have cancer. But if somebody were to say, oh, well, what was the result of your test? You could say, oh, what was positive? Well, what is that? I mean, it was good. So depending on your stakeholders, sometimes you have to use positive and negative in a different way. So in that, perspective, positive is not rejecting the null. Positive is finding support for the null. And we will never use this perspective in this class, but you should just know that outside of class, you really got to calibrate with your stakeholder so that when you say oh, we detected something, or oh, the test was positive, that you both know what you mean by positive. So there is no one definition of positive and negative. As you slide the continuum towards the statisticians, then positive means you detected a difference from the null. I think usually as you slide the scale more towards a lot of stakeholders, it's the opposite. So I just want you to be aware of that. And it's not a right or wrong. It's just a different cultural thing. And you just got to calibrate. You got to code switch depending on which community you're in. That's why I dislike talking about the null, because there's no ambiguity there. So that's why we have these ugly terms like type 1 error and type 2 error, statistical power. Nobody's confusing those. Those have one definition. So you might be tempted to say, oh, we got a positive result, we got a negative result. But there really is value in using the jargon, because then way nobody's confused. Okay. So any questions about those interpretations? Positive, negative, type 1, type 2? Okay. All right. So like I said, this time of season is all about alpha and beta. The thing that goes bump in the night, like any other time of season, the thing that goes bump in the night is the water heater kicking on. But this time of season, the thing that goes bump in the night is some spooky, scary thing under the bed or something like that. So, the whole Ghostbusters franchise, it was about a set of people that are here to believe you. What does it mean we're here to believe you? That means that they are willing to tolerate an alpha that is relatively high. So they are more worried about squashing the beta. They do not want to, they are not worried about finding extra detections that aren't there, because if they optimized for alpha, they would miss things that really are there. So that's what I mean. Like in engineering, we're very much this way. In engineering, we often have bigger R&D budgets than they would have in science. So we are ready to believe you. We're ready to look for the potential effect. If we work in R&D, we have to have a report of potential directions that our R&D can go in, and based on our kind of confidence. And so we crank the alpha up because we trust that when we see odd anomalies, what might be anomalies, we flag them so that if there is budget later, we can investigate them to maybe turn that into a new product that gives us an advantage over our competitors who never saw that weird oddity there. So it's a little silly I bring up the Ghostbusters here, but I'm just trying to specify that depending on your job, you will make different decisions about how much risk you'll tolerate in which of these bins, alpha and beta. And the ROC curve, the ROC curve, which I'll show here in a second, it shows that there's a trade-off between alpha and beta, that if you push alpha down, you'll push beta up. If you push beta down, you push alpha up. So you have to choose, am I more on the alpha side or the beta side? And so this community cares less about alpha. They crank it up because they really want to push beta down. But you might be in a community that goes the other way. So engineering is oftentimes more this way. We're okay detecting things that aren't there because we can follow it up. A lot of scientists don't have the opportunity to follow it up, or they have to be very careful because, somebody's going to put out a press release and it's going to say that jelly beans cause cancer. And that's going to go, the media is going to pick it up and people aren't going to eat jelly beans again. And they say, oh, sorry, it was a false positive. And so, in that case, you really want to say, before we come out and make policy advice, where no one else is going to have the money to be able to follow us up and test the study, to reproduce the study, we have to get it right on the first try. And if you have to get it right on the first try and no one's going to follow it up and it's going to have you very high stakes, you push your alpha down. So the stakes of the problem and whether someone can reproduce it afterwards helps you determine how to set these. All right, questions about that? Okay. All right, so I mentioned the ROC curve, which we introduced last time. And I also said it comes from this graph here. Hopefully you've seen this one before. This is this idea that this blue curve up here, this is the distribution of values we would expect if the null hypothesis were true. So this thing on the left, that's if the null hypothesis is true, we'll get values anywhere in this range. Now, an alternative hypothesis might be over here, and its values are this range down here, which overlap with our null hypothesis range. So that is what defines our 4 boxes for our false negatives, false positives, true negatives, and true positives. They are where these things overlap and do not overlap. So the things, if I were to set a threshold, like this magenta line, this purple line going up and down here, this threshold is based on what evidence I've measured. I'm going to say things to the left of that line are negatives and things to the right of that line are positives. So things to the left of that line that come from my null distribution, those are true negatives. But there are a few cases here that come from my alternative that happen to be low enough that they go under that threshold. Those are my false negatives. To the right of that line, anything that's in that alternative distribution that is not in the null distribution are my true positives, and anything that is to the right of that line but comes from my null distribution are my false positives. So as you slide this vertical bar to the left and to the right, you go along the ROC curve. And so that's where the trade-off between alpha and beta comes from. This picture right here. So that if you want to reduce your false negatives, how do you do that? Well, if I move this thing to the left, then I get rid of the false negative error. But what happens as I move this thing to the left? Well, if I move it to the left, it necessarily increases the false positive area. So that's where that trade-off comes from, this picture right here. And we can summarize that in these ROC curves for any test. And we plot alpha on the x-axis and 1 minus alpha, or sorry, 1 minus beta, which is our power, statistical power on the y-axis. And what we find is that every test will be in this upper portion here, and they will trace out a line that has a bend in it like this. And as you move your threshold, and so this is like your chi-squared critical value or your t statistic critical value. Those critical values you look up in the back of the book, they are this threshold. And as you crank them left and to the right, then you move this point along the ROC curve. And most of the time, we just tell you an alpha of 0.05. And so that would mean we're going to find the threshold that cranks this thing down to where it hits 0.05 down here. So when it hits 5% down here. And that's just going to have some statistical power with it. If you want more statistical power for that alpha, your only choice at that point is to either get another test or increase the amount of data. Because there's just no other, you live on that curve for this particular test, for that curve, for that amount of data. And so, again, alpha and beta are coupled. You can't decouple them. You have to get more data or a new test. But this curve comes from there. All right, any questions about this picture? Everybody understand this overlapping set here? And we're going to see more of this today so that it maybe makes that clearer. Hopefully, at least this part is a little bit of review from 380 or 385. Okay, all right. So great example of that t-test. You're going to be using the t-test and doing a power analysis on it for question 2 of your homework, the current homework. We introduced this last time. Again, most of this hopefully review, seen this before. This is your t statistic where we have a null hypothesis, which is just a fixed value here. Somebody says, I think the null is here. I'm testing to see, is the mean equal to 5? Exactly. Someone comes to you and they say, that's the null, it's 5. Doesn't come from another data set or whatever. You don't have to calculate it. It's just assumed out there. Somebody says, you know, if things are normal, the mean should be 5. Take some data, tell me, do these data seem like they come from a distribution that has a mean of 5? So you just pick that out there. That's your null. And then the other side, that's your sample. So remember, this is a one sample t-test. That means that we have one thing that is derived from data in the numerator here. There is a 2 sample t-test where instead of saying the null is 5, you say, do these two distributions, these two populations have the same mean? I don't know what that mean is, but do they have possibly come from the same distribution? And in that case, you would have like a Y bar here and then an X bar here. But here, we're just fixing this. And that's what makes it a 1 sample t-test instead of a 2 sample. So in order to make this work, what assumptions do we need or where does this come from? Well, we're going to make the assumptions that every data point is independent from every other data point. If you can't make that assumption, you can't use a t-test. So before you use a t-test, you have to ask yourself, do I have independence? The other assumption is that all of your data are normally distributed. The rest of this is going to depend on this critically, that they're normally distributed. If the data aren't normally distributed, you can't use a t-test. It turns out if you have a lot of data, the t-test tends to still work pretty well. But t-tests are typically used when you don't have much data, in which case it's critical that the data are normally distributed. So before you even can do a t-test, you have to test to see, are my data normally distributed? That's why we have high-powered tests for goodness of fit for normality, like Shapiro-Wilk. So then where does the math come from? Where does that formula come from? Well, we said we're going to take a sample average of our data. So we've got our data. We took n samples from our data and we divided by n to get our sample mean. And so we can say, well, that sample mean, that's never going to equal our actual population mean. That's kind of the whole point here. It's just going to be an average, an approximation of the real population mean. So that is a random variable. And so we can ask, what is the mean of the sample mean? What is the expected value of the arithmetic average? So that's what we've got here. And if we say, what's the expected value of each one of these little points? Well, that's the mean of the population, assuming the null is true. Then the mean of this whole expression is just also going to be the mean of the population. If you just take all of these things, since they're all divided by n, the n's cancel, and you get that mean of that population out. So if we create a new random variable where it's just this value minus our null, then the expected value of that random variable should be 0. So every time we calculate this thing from real data, it won't be 0. But if the null is true, it should cluster around 0. That's the idea. And so what we're trying to get to is to a point where if it is not 0, how far away from 0 does it have to be for us to conclude that our null must be false? That's what we get, what the t-test is building up for. In order to do that, we have to scale by the variance we're seeing. So then you have to ask, what's the variance of this thing? Or more importantly, what's the variance of this variable right here? And so you can do some probability theory and you can say, well, what's the variance of each one of these? Turns out that it's equal to the variance of the underlying null population divided by n squared. There's a squared term there. That's really important. And so with that, you can calculate the variance of this thing. It turns out it's the sum of all these variances. So then that variance divided by n squared gets multiplied by an n, so you'd lose one of the n's in the denominator. So the variance of this here, this y bar minus mu, that variance just becomes the variance of the population divided by n. So we're just cutting the variance of the population by how many data samples we have. So the real distribution has got this much variance. Our estimation of the mean is going to have n times less than that in variance. So then the standard deviation is just square root of that. And this formula is a famous formula. This is the so-called standard error of the mean, or the SCM. So as you start, if you haven't already been introduced to this, if you start looking at bar plots where they show error bars, this is often the choice for the width of those error bars, the standard error of the mean. It's not the standard deviation of the population. It is a scaled down version of it that captures not only the variance in the population, but how much the population's been sampled. Because the more samples you get, the more you get a high confidence in your estimate of the mean. And so that's why this thing collapses to 0 as you get more and more samples. That's what we mean by the standard error of the mean. It's not the standard deviation of the thing that you're sampling. It's the standard deviation of the estimate of the mean. And that estimate gets better and better with more samples. And so that error gets tighter and tighter. So we've got those, that critical quantity here, the standard error of the mean, which we're now going to make use of. Any questions of what I mean by the standard error of the mean, the SEM? So again, that's oftentimes what you see in error bars on bar plots. Okay, so now that we've got that, then we've got our expectation here that this variable, our sample mean minus the hypothesis, that should be near 0. And the standard deviation of this thing should be this quantity here, the standard error of the mean. Now, if we take the number of samples to infinity, then it turns out that this arithmetic mean, because it's got a sum in the numerator, by the central limit theorem, is going to go to a normal random variable. So this thing should be normally distributed with lots and lots of samples. And that normal distribution will have the mean of the population and this standard deviation. And we can subtract off the mean, and we get now a zero mean normal distribution with this standard deviation. And that's really nice because now we can standardize it. So that's what we do here, is we're saying that with very, very large numbers of samples, this t statistic is just the standard z-score for this normal distribution. So that's what we've got here. This is just going to be a z-score. You know, or in other words, t is going to be distributed as a normal distribution with mean 0 and variance or standard deviation 1. So that's the idea here. So with large amounts of data, this becomes a z-score. And we already know how to deal with z-scores. If we want to see, are things too far away, then we just say, well, for a standard normal, we know what the threshold should be that represents 5%. You know, it's 2.5% on one tail, 2.5% on the other tail. That threshold, because it's symmetric, that'll be the same threshold on both sides. So if we compare the absolute value of this thing to that threshold, then that will tell us how far away we need to be before we hit 5%, before we hit an alpha of 5%. So that's how we get the t statistic for large samples. But then the question is, which Guinness was facing when their industrial statisticians were trying to figure out how do we do process improvements without spending a lot of money on huge amount of samples on test treatments. Then they said, well, how do we do this for small numbers of samples? What does this look like when we can't determine or we can't depend upon the central limit theorem? That's where we got the student t distribution. And so that's this. So a little more math that I won't go through out of scope of this class, but this is the standard normal, this blue curve up here. This is the student's t distribution when you only have 1 degree of freedom, which means you only have 2 samples. And so I remember that 1 degree of freedom that comes from because I'm calculating the mean. Once I fix the mean, I've effectively borrowed one of my data points because I can solve for the other data point. That's where I lose my degree of freedom. So 2 samples is 1 degree of freedom. And so with only 1 degree of freedom, so in other words, if you calculate this, the distribution of this value, if you go out to a normal distribution and you take 2 points and calculate their mean, and then another 2 points and calculate their mean, and another 2 points and calculate their mean, and take all of those means and you put them into a distribution, and you do this operation to it. So all of those means, you subtract off the known mu from your normal distribution, and you divide by the known standard deviation divided by square root of n. You calculate this for every one of those 2 sample means, and then you take the distribution of the t values you get out, then you get this t curve here, this red curve with its fat tails. That's the key property of a student's t distribution, is that it has much fatter tails than the normal distribution. Normal distribution lays right down. The t distribution, it will have values that are large and small more often than you would expect from a normal distribution. In other words, small sampling, the bad luck of using few samples introduces variance, which creates these extra tails. So if I had lots and lots of data, things are just going to snap to the normal distribution. But what we're seeing here is the background normal distribution plus the bad luck of, well, I just happened to grab 2 data points that were very close to each other on this far end of the distribution. Or I got another 2 that were on this far end of the distribution. So that small sample noise is popping up these tails, and that's why we have a different distribution than the normal distribution for small samples. But as I increase my number of samples, so 2 degrees of freedom, notice I've gone now from this green curve on the previous one to this new red curve. The red curve is the highlighted one. It's always going to be the one that I'm looking at on the slide is always the red one. It's closer to the normal. As I keep going, so now I've got 3 degrees of freedom, so 4 data points. It's even closer to the normal, and so on and so on. And asymptotically, by the time I get to about 31 data points or so, 30 degrees of freedom, it looks pretty normal. And so once you have about 30 data points, at that point, you oftentimes don't need to use a t-test. You can just go to a standard normal. Calculate a z-score. You don't have to worry about the sampling stuff anymore because it's probably going to be pretty much normal. You still can use a t-test, but at that point, the t-statistic basically becomes the standard normal. All right, so that's the logic behind the t-statistic. That's why we have it. It's for us to extend the logic we've learned about z-scores into the low sample regime, the low sample range. Any questions about that? Okay, so we call this a pivotal quantity. This is a statistician's term. That means that its shape only depends on its degree of freedom. It doesn't depend on the particular null hypothesis you pick. That's what allows us to set these easy thresholds. So you can always say that regardless of what hypothesis, remember our hypothesis is just on the parameter, the mean. So regardless of what mean you pick, then this thing is always going to be a measuring stick where we can set a threshold to say, oh, you want 5% alpha? Well, 5% alpha corresponds to 1.96. That would be the z-score equivalent. This one, it will be larger than 1.96 until you get large sample sizes, and then it will converge to that 1.96 value that I said you'll all eventually memorize. So that's the idea here. And because it's a pivotal quantity, its shape doesn't change with the more data you get. But what happens is that there is a t-distribution for your null hypothesis, and there is a t-distribution for the alternative hypothesis. And the difference between those two t-distributions is affected by how much data you have. So that's kind of what we've got down here, is that this is, in that picture, I think maybe I have that picture here. Imagine both of these curves, this bluish curve on the left and this reddish curve on the right. Imagine those are two t-distributions. This is the t-distribution for your null hypothesis. It's right at 0. And then if you have an alternative hypothesis, it's like, if the null hypothesis, if the null was, a 5, and then the alternative that was actually real is a 10. So there's a 5 point difference between them. Then we center this at 5. And then this thing is 5 over. Well, so these things are always going to be separated by that much. But then as you increase the amount of data, then what this little math does down here is it basically makes it so that that red curve gets farther and farther and farther away. Its width doesn't change, but with additional samples in T space, it's like we're in this universe, but if we were to then go through a portal to the T universe and see how we're represented there, in that space, the number of data points you have sets the distance between things. And so if you get more data here, then what that's going to end up doing is it's going to take this red curve and it's going to move it way away from the blue curve. And what does that do? It takes this little false negative triangle and it moves it out, making your false negatives go way down. And that allows you to play with your thresholds here, allowing you to get fewer false positives. So you can adjust the thresholds and you got less of an impact of that trade-off. In other words, as you get more data, if we were to look at this ROC curve, this magenta line gets pulled up towards this corner. Because imagine if this magenta line followed this edge and then went to this edge here. You just pulled it all the way and you just inflated it to fill the box. In that case, there would be no trade-off between alpha and beta. The closest thing you can get to having no trade-off between alpha and beta is having an infinite amount of data. And that's because it takes this alternative hypothesis and it moves it so far over that, that there ends up being basically no overlap in the tails. And if there's no overlap in the tails, you don't have to worry about getting it wrong because you just have to focus on the null, how nully you are. And you don't have to worry about how the interference from alternatives. All right, any questions about that? Sort of trying to visualize what we're doing with the stats when we take more data, when we adjust alpha and beta. I want you to sort of start getting an intuitive feel of what's happening in the stats. and what that means for the results of the stats that come out of that and how to interpret them. Okay. All right, so back to the puns. Halloween again. So this is, I think, a biometry student, is a PhD student, goes out, he makes this shirt. Notice a t-shirt here. Down here, it's hard to read, but it says student. And then it's got this distribution painted on the shirt here. And so the challenge here is to explain the joke. You might say, is this a normal student? For more context, this isn't the only effort. He didn't even just get a t-shirt and put some electrical tape on it. The additional thing is he carried around with him a box of tea and carried around a Guinness. So he always had those things with them there. So the Guinness, of course, is a reference to William Seeley Gossett, the industrial statistician at Guinness. And then hopefully the tea you see is a reference to the tea test. So what's the joke here? Does anybody see it? What is he wearing? Keep in mind that he himself is a student. So what's the joke? So students' t-test, good eye t distribution, fat tails. If this is a normal distribution, it would have come all the way down to the axis. So, but where did he put the t distribution? On the shirt, thus student's t-shirt, right? You might also say not a normal student because this is not normal. So I once saw some artist post something on Twitter, I think Twitter at the time, where they are admiring some architecture of this church that happened to have this shape. And they said, this beautiful symmetric shape. It's beautiful to see the Gaussian form in architecture. And of course, because it is the internet, it was just filled with comments where people were saying, that's totally not a normal distribution. That is much closer to a t distribution. So you see fat tails like this, you think, okay, that's not normal. It's probably a t distribution. So that's the joke there. Those are the fat tails. There's the red curve there, and so on. So there's still time for you to make this costume. So just think about this for the weekend. All right, so I've mentioned to you that whole derivation I gave you, it was critical that the distribution was normally, like the data that you were testing was normally distributed. And that really helped gain power. How does that gain power? It's because we know what the alternative looks like. If we make the assumption, we make a commitment that the data that we sample are normal, we don't know the mean, but we know it's normal. We're just testing whether we know the right mean, but overall, we're testing that it's normal. And we're assuming that we there's kind of some assumptions about equal variance between groups. So in that 2-sample test that I was talking about, you would have to assume that if you have this population, data from one population, data from this population, they have the same variance. So they're both normal and they both have the same variance. And then you're testing whether they have the same mean. If we can assume normality and in the 2-sample case variance equality, then that gives us so much power because we know what the alternative looks like. It is also normal. So we can draw that little diagram that I had there and do math on it. And with that math, it makes it very easy for us to calculate basically those operating characteristic curves to do our power analyses. So that's if we can assume normality. We refer to this as a parametric test because we are not trying to guess what the distribution is. We're trying to guess what the parameter of the distribution we're committed to is. So we're saying, like, I took a bunch of data. I know that data is normal. I'm going to say that is normally, I just don't know what the mean is. So I'm going to say that if things are going as planned, the mean should be 6. So all I care about is what is the mean. Is it close to 6 or is it far from 6? But I know that it's normally distributed. So it's a parametric test because I'm making an inference about a parameter, the mean. I'm not making an inference about the shape of the data because I take that as given. Now, that often isn't the case. You're going to look at data. Fortunately, in this class, for most of the things that come out of ARENA, the data, when you take a histogram of them, they're going to be able to fit. They'll match this. But in the real world, you're going to find data sets where you can't immediately, they aren't normally distributed. And so if they aren't normally distributed, you can't use t-tests, ANOVAs, and so on. You can do things with those data to try to make them normal. So you can run them through a logarithm, for example, and then you look at the distribution of the log transform data. Is that normal? And so on and so forth. But in order for you to use this high-powered machinery, you have to get things into the distributional assumptions. And then you can make an inference on the transformed data. But if you can't do that, that's just not available, then you have to resort to what we refer to as non-parametric tests. So these are tests that do not assume a distribution. So they work with the raw data without any or with very few assumptions. And so there are non-parametric, this is versions of each one of these parametric tests. So if you feel like, oh, for this particular study, I would like to use a t-test, but then I found out that I can't use a t-test because it's not normally distributed. What do? Well, you Google non-parametric t-test. And when you Google non-parametric t-test, it will say that's a Mann-Whitney U test. TU, one more in the alphabet, so that's not kind of a mistake. So the U test is identical basically to the t test. It's a different formulation, but it doesn't make any assumptions about normality. So if you want to test equivalence in means or medians, and you don't have normality, then in your statistical tool, in your JUMP, in your SPSS, in your R, any tool that has a t-test will also have a u-test. And that's why they have multiple tests. When they go to there'll be like a test menu. You go to tests and it says, you want to use a t-test for these data or a u-test for these data? Like why, what's the difference? The difference is that if you can meet the assumptions of the t-test, you get more power. If you can't, then use the u-test. It will look for a difference, but it might not find one. And that's just because it's a lower powered test. So if you can make these assumptions, it's more likely to find differences. But if you can't, there are fallbacks. And that's what's down here. So these are kind of outside of the scope of this class, but I just mentioned them because anything we talk about in this class, if you find yourself in a statistical problem later in life, and you're like saying, Ted only taught me a t-test. Ted only taught me a paired difference t-test. Those sorts of things. Don't fret. Just Google non-parametric thing I taught you, and it will give you the non-parametric version. So from the T to the U, from the paired T to the signed rank test, from the ANOVA to the Kruskal-Wallis, all of these tests down here are just low-powered versions of these tests that don't have any of those assumptions. So just keep those in mind. You don't have to memorize this correspondence for this class, but I do want you to know the terms parametric and non-parametric and the difference between them. Because there will be a time in your life, if you're doing any stats, where you're going to say, I need something like a t-test, but none of my data work for that. What do I do? And just knowing the term non-parametric will allow you to find the solution. All right, any questions about this general idea? Parametric versus non-parametric. Okay, great. So now this is much more like number 2 in your homework. So we already talked about the power analysis for a general t-test last lecture. But in your homework, I actually asked you to do a paired t-test. What's that all about, and how do we do the power analysis there? And where does a paired t-test come from? So this is the setup that's very similar to the homework setup. So we have, instead of generating input data with a sim, we have historical input data. So somebody's done, like the thing that maybe some of you are doing this week for your input modeling report. They've gone out to the system of interest, the business, the factory, whatever, and they've taken input data. Let's say it's arrival data. So they know the time between every customer who's arrived. Real historical data on this day at this time, someone arrived at this time, and so on. So normally what we would do is fit an input model, get the parameters of that input model, tell Arena what those parameters are, and then Arena will then generate fake customers that statistically are similar to the customers in the real world. But for this here, we're saying, we actually have real world data. Let's just pipe the real world data into the sim and get rid of the random number generator. So we're actually going to run customer one's interrival time, customer two's interrival time, and so on into our create block as a data set instead of drawing numbers. And then that way, we can hopefully compare apples to apples in terms of our performance. So if we run the exact same customers into our sim and we get very, very different output from our sim than the real world, then that gives us some idea that there's something very wrong with our sim. If we just had our sim generate new inputs, then we're going to get some difference between our sim and the real world just because it might just be bad luck. It might be the day that we went and captured data from whatever, from Chipotle or Panda Express or whatever. It might be that day was just a really bad day, and it's not a typical day for this particular restaurant. But maybe you just want to say, for that bad day's worth, for that real day, what would our sim do? You pipe that thing in without the random number generator. So run the real input data in, not random numbers, directly into the sim. And then each sequence of real data, so let's say this is Monday's data, Tuesday's data, Wednesday's data, et cetera, so on. So we're going to have Monday in the sim, Tuesday in the sim, Wednesday in the sim. Each real day's data generates a data point in the sim that you can compare to the data point from the real world. So you can say on Monday, the average wait time was 5.6 minutes. On Tuesday, the average wait time was 6.7 minutes. On Wednesday and so on in the real world. And then you simulate Monday using the same customers. And you'll say Monday's sim data is whatever, Tuesday's whatever, Wednesday's whatever. And now we can compare those. But we're going to pair them up by their input data set, similar to what we did in the muffin sim. So this means that the data points here are not independent from the real world. Normally, we would generate new random numbers here, and the data we would get out of the sim would be independent from the real world. They'd be set by the same parameters, like, on average, people arrive 5 times an hour in the real world and 5 times an hour in the sim, but the actual customers here would be independent of the actual customers there, in which case we would use a 2-sample t-test, compare that population to that population. We would say, what's the average there? What's the average there? Is it possible that these two distributions have the same average? That's a 2-sample. But we can't do that here because every Monday's data generated 2 data points. It generated the real point and the sim point. Tuesday's data generated a real point and a sim point. Wednesday, real sim. These are coupled. So I can't just treat this as 5 independent data points from there. These are 5 pairs of data points. Real sim, real sim, real sim, 5 pairs. So I can't use a 2-sample t-test. That's what we're saying here. So what do? In every pair, I measure the difference. So I say on Monday, the sim beat the real by 30 seconds. On Tuesday, the real beat the sim by 1.5 minutes. On Wednesday, and so on. So I calculate the performance difference for every input data set. So instead of getting 5 pairs of data, now I get 5 differences. And that's the so-called paired difference t-test. So we're going to be doing a 1-sample test on these differences, real minus sim. And if my sim is very similar to the real world, then I should expect the population of differences to cluster around 0. I should not be able to detect a difference from 0. And if I can detect a difference from 0, then that means that my sim is a bad match for the real world, and I need to recalibrate my sim. All right, that's the setup. Any questions about that difference in experimental design and the consequences for what statistical test we use? You can't always use a 2-sample t-test, and you can't always use a paired t-test. You have to design the experiment for the test, or pick the test for the experiment. Okay, so for what's nice about this, and this is what you do in your homework, is a power analysis for a one sample t-test is pretty easy. We did that last time. All that I'm adding on here is this pairing here to try to then bring it all the way to what we were doing in that homework assignment. So, and I also want to notice here that, or note here, and we're going to talk about this, not next unit, but the unit after that, but this idea of pairing is a way to reduce variance. So it's a so-called variance reduction technique, or a VRT. And so this is fits within a bigger group of techniques called blocking techniques, statistical blocking. And these are methods for reducing variance in experimental designs. So this is just an introduction to that. If you take a more advanced stats class, you'll learn about all sorts of different ways to block data and how you can build more sophisticated statistical tests to make use of those blocks. This is like the simplest form of that. Okay, so this is just like your homework. So you've got the system output and the simulation output. These are, again, you can think of this as a Monday, a Tuesday, a Wednesday. So for every day, we had a certain set of customers, and we measured in the real system, for example, what was the average wait time. And then we use that exact same set of customers and we put that into our sim instead of a random number generator. And we said for our simulated customers, what was the average wait time? So we've got a bunch of average simulated wait times and a bunch of average real wait times. So our first step is to then calculate the observed difference on each one of those data sets. So this is my Monday difference, my Tuesday difference, and so on. I then, because I know I'm going to calculate standard deviation, can say now that if once I get the average of all of these, then I can take that average, which I've got here as D hat, or sorry, D bar, and I can calculate the squared deviation from the mean so that I can end up calculating my variances. So that's how I fill out this table. If these I'm basically testing to see, is this population of differences, is it close enough to zero for me to say that my sim is a good representation of the real world? So I calculate my D bar, my average difference. I calculate my variance of that population. And then I do a one sample t-test on this one sample here. So the real question here is D bar, is it close enough to zero? And so this is my t statistic, where this is the standard t statistic, but remember the mean, the parameter I'm testing for is just zero. So my t statistic just becomes the average difference divided by the standard error of the mean, divided by this standard deviation. So this square root of this divided by the square root of the number of input data sets. I want to emphasize that this is not the number of total data points, which would be 2K. This is the number of pairs. And there are K pairs, so that's why it's a K down here. All right, so from here, I can do my one sample t-test. I can just calculate this thing. I look it up in the back of the book. I see what the critical values are. And then I can say, are these far enough apart? If they're close together, then the real question is, did I gather enough data to be able to conclude that just because they're close? Remember, in those kind of those two humps that diagram where we had the two different distributions, I said the more data you gather, the more you shift these pivotal quantities away from each other. Well, the less data you gather, the more overlap you get. And so not being able to detect a difference might just mean you don't have a lot of data. And so the question is, do I have enough data for me to trust a failure to reject the sim? And that's the power analysis that you're going to be doing on question 2 of that. So how do you do that? What are you going to do for that? Well, in order for me to move forward with that, I need to know what is the smallest distance that you view as important. So if I go to the owner of Panda Express and I say, I'm going to build a simulation of Panda Express so we can do a bunch of tests on the new ways for you to lay out food or distribute workers or whatever, but we need to build an as-is version of Panda first, then at what point are you going to be satisfied that our simulation is close enough to the wait times that your customers see? And they might say, well, as long as it's within 2 minutes. then I'm going to say the sim is close enough. So that 2, that is what we're going to take here is this D. So this is in real space, what is the minimum difference that you need to be able to detect? If it's less than 2, we don't care about detecting it. But if it's more than 2, we need to make sure we have enough samples to detect that it is down to 2, but we don't need any more samples than that. So if it's more than 2, we'll have plenty of samples. If it's down to 2, we'll have plenty of samples. If it's less than 2, we don't care. We may not have enough samples for that. So we ask them for that, and then we standardize it by dividing by the standard deviation of our difference data set, which we've already calculated here. And that gives us the so-called effect size. Now, we're going to set a desired statistical power at 80%. That's the conventional choice, but you could, on your job, somebody could say, we actually need a statistical power of 90 or, whatever your comfort is. So, but in this case, we're going to set it to 80. I think that's what we did on the homework. And then we're going to look at these OC curves. These are different than the ROC curves, but they plot similar things. So in the back of the book, for a two-sided one-sample t-test, they have 2 OC curves, one for a 5% alpha, the other for a 1% alpha. Make sure you look at the right one, which is this one over here. We'll zoom in on that. And so you're going to calculate an effect size, which will be the x-axis. And then we have a statistical power of like 80%. Well, that's a 20% type 2 error. It's just 1 minus the statistical power. So then you just look to see where your effect size intersects your desired beta, your desired type 2 error. So we're going to be looking along this 20% line. And so we can see that if we have an effect size of 1, we're going to need 10 samples. If we have an effect size of a half, we're going to need 30 samples. So the smaller the effect that you need to be able to detect, the more samples you need. That's why this gets higher and higher as it gets closer to this origin point here. And that's how we do our power analysis for the paired t-test. Any questions about that? That's like identical to what you'll be doing on question 2 of the homework. Okay. Okay. All right. So I just want to mention briefly chi-squared, so you know where the 5 comes from, the 5 that's in every bin. Well, what is a chi-squared test? So remember, it's basically we're counting a number of things that land in bins minus things that we expect to land in bins, and we create a score based on how far away each one of the observed counts are from the expected counts in each one of those bins. That's the chi-squared score. So big chi-squared is bad or is very different from null. A low chi-squared is very close to the null. So where does this come from? Well, so if I have in the binary case, so I just got 2 bins, this is my chi-squared statistic here. Okay, so let's see where that comes from. So in that specific case, instead of using a chi-squared, you could use a binomial test. Remember, binomial is discrete, so it is the number of counts. So a binomial test is like, how many times does a weighted coin come up heads or tails? And if I know that I flip it 100 times and it comes up heads 75, it had to have come up tails 25 times. So I really only have 1 bin. The other bin doesn't really exist. Same with a chi-squared. So even though you have 2 bins, you only have 1 degree of freedom. So we can replace, for the 2 bin case, our chi-squared test with a binomial test. And so then we're saying we have expected probabilities. What's the probability you go in bin 1 or bin 2? For the number of total trials, you can then say, what are my expected counts for bin 1 and bin 2? And then compare them to observed counts. And so in the binomial test for this particular case here, the expected that you find in the first bin is just the number of counts times the probability times how fair the coin is. And then for the second bin, or for the, and then so that's the expected that I find in that. I can approximate the binomial by a normal, and the variance of that normal is going to be this expression over here, np times 1 minus p. So we often for convenience, approximate binomials by a continuous distribution, by a normal, because normals are just easier to deal with. But this approximation, as we'll see here, in case I run out of time, only works if NP is 5 or greater. So as we're about to see, the chi-squared test is built off of this approximation, approximating a binomial by a normal. That approximation only works if the expected count in the binomial is 5 or more. If you don't have that, you can't make this approximation. And if the binomial is not approximated as a normal, then it doesn't bubble up into the chi-squared. So how does that unroll? Well, if the binomial is approximated by a normal, then we're going to create effectively a z-score here, or a standardized score, where we've got our expected count in the bin, our observed count in the bin, divided by the standard deviation, which if I plug in these things, ends up being this. Well, this is our z-score for how many things land in one of those two bins. Well, that's convenient, because if I square that, then I get this quantity. And at some point in some math class somewhere, you may have done partial fraction expansion. If you haven't, a lot of people taking a systems class, you had to do it a lot. But there's basically whenever you see a fraction that has a product of something in the denominator, there's a way to then break it up into the sum of two fractions that have a simpler term in their denominators. That's what's called partial fraction expansion. And so when you do that PFA of this thing, you get this. And if you look at this, this is the chi-squared statistic. So I'll move forward. So like if I go back here, M, that's the number expected in one bin. N minus M, that's what's expected in the other bin, because they add up to the same number. I'm sorry, that's the observed counts. Observed in one bin, observed in the other. This is the expected count in that bin. This is the expected count in the other bin. So that is the chi-squared statistic right there. So 1 degree of freedom, 2 sums right there. That's where the chi-squared statistic comes from. And it turns out that generalizes. So it's, again, 1 degree of freedom, but 2 bins. And that generalizes to k minus 1 degrees of freedom from k bins. And that right there is the chi-squared statistic. It is this idea that, so the chi-squared statistic, where do we get that statistic? Where does that quantity come from? Where did somebody come up with that distribution, that chi-squared distribution? It is the sum of standard norms. So if you take an N01, a standard norm, and you add another standard norm and add another standard norm, you add those 3 together, that's described by a chi-squared statistic. So with, I think, in that case, 2 degrees of freedom. So that's with 3 degrees of freedom. So that would be your 4 bins. So that's the idea here, is that the way they solve for the chi-squared distribution is by taking the standard norm, similar to what Gossett did with the t-test. We build everything off the standard norm, and you add standard norms together, and you square them, and you get the chi-squared distribution. So that's where this thing comes from. And that's sort of, but this all depends upon this approximation of a binomial distribution by a normal. And that only happens when the expected counts for the binomial distribution are 5 or more. If it's less than 5, it doesn't look like a normal at all. And your chi-squared approximation is not going to look like a binomial test at all. So a chi-squared test is approximating a binomial test. It does that by way of a normal, and that only can happen if you have 5 in the expected counts or more. That's where we get these shapes. And so these are your chi-squared distributions. Each one of them, if you drew random standard norms in MATLAB and added them together and squared all of those values before you added them, and then took the histogram, you would get these things. That's where the chi-squared comes from. All right, I don't keep you much longer. So happy to take questions after. Let's get to one of the, and then we'll talk about Bonferroni next time. So we'll talk about, let's just do the attendance. All right, so question here is, If you raise alpha, what happens to beta? And that's all I've got. So if you increase type 1 error, what happens to type 2 error? Does it go up or go down? Increase or decrease? And otherwise, I hope you have a happy Halloween and a good weekend, and we'll see you next week.